You are listening to Science Coast with Mallory Havens and
Chris White.
And today our guest is
Mike McFerron.
Hey, Mike, can you tell us what your role at the university is?
Sure. I am professor of music. I'm the chair of the music department. I am co-director of Arts and Ideas, and I am Lewis University's composer in residence.
I am actually quite jealous. For a long time in my life, I have thought of myself as a musician, an amateur musician, a musician wannabe. I've spent a lot of my time hanging around actual musicians who know what they're doing. I'm a part-time trumpet player. Anyway, today we thought that we would talk about the interdependencies, interconnections, the overlaps between music and science, with the understanding that in the physical sciences, and I'm a physicist, so many of the people that I know in the physics community play an instrument. And it just seems to be there's a natural connection, whether it's math or whatever. So, Mike, curious what you think about that.
Well, yeah, I mean, there's several, typically, I don't know, Mallory, but it does seem like it's mostly physicists that are musicians. You know, everybody knows of Einstein.
I agree with that.
Right? I mean, everybody knows of Einstein and violin, or Feynman as a bongo player, right? My favorite was Heisenberg, and most people who knew him mostly as a pianist, not as a physicist, like in his Neighbors, and things like that, right? Yeah, I mean, we know him as
That's right. His physics was quietly done on paper. His music,
yes. But I mean, his music was his vehicle that he used how he met his wife. And so I've always liked him. In fact, I wrote a piece. It's called Delta P Delta X is greater than or equal to Planck's constant divided by 4 pi.
I love that.
Any questions?
Yeah, what does it sound like?
Yeah, well, it uses piano samples. It was actually written several years ago, and it's dedicated to Leonard Wiesenthal. We have the Leonard Wiesenthal lecture series. Mm-hmm. Me and Len would take students to the Compton lectures, which are actually going on right now at the University of Chicago till April something, May something. And so we would get up on Saturday morning and we would drive down to these series of lectures on a Saturday morning with students. And the first couple of times we would go down, several students would go with us. And then as the lecture series continued, fewer and fewer students showed up until it was just Len and me. And we had a great relationship. Len actually did a radio show on classical music here at WLRA. And all the way down, we would talk about classical music and what interested him. And then we would go to the Compton's lectures. And on the way back, he would explain to me what was just done at the Compton lectures, because 90% of it went over my head. But
what was that lecture series about?
Well, we did it a few years in a row. The one that where this piece came out of was on light. It's a lecture series done usually by a postdoc fellow at the University of Chicago, and it covered everything from light as being a wave, as a particle, to all the way into entanglement.
Oh, okay.
And one of the things that came out of there was the Heisenberg Uncertainty Principle, and it wasn't new to me, but it was explained in depth to me on those drives back. And so the equation that I just gave was delta P delta X is greater than Planck's constant divided by 4 pi, which, by the way, is I didn't make that up. That is the Heisenberg Uncertainty Principle formula. And there's a lot of connection, I think, between it and music, and it's why I wrote it. It's a fixed media piece for where I just use piano samples. And what I like about the Heisenberg Uncertainty Principle, so please correct me if I'm wrong in my understanding of it, but the Heisenberg Uncertainty Principle is used in quantum mechanics to talk about subatomic particles. And basically, it says that we can know the location of a subatomic particle, but we can't know its state, right? Is that correct?
Close enough.
Close enough. I mean, look, it's a musician's approach to the Heisenberg Uncertainty Principle. But in music, you can think about that in the same way. As music is being played, you can know where you are in the piece or you can stop it and analyze what's happening at that moment, but you can't really know both as the piece is happening. And so, again, I'm not the first person to make the connection between Heisenberg Uncertainty Principle and music and how we perceive it. But I did try to, I guess, in my piece, think about that in, I think, interesting ways. And so a couple of the things that I did was I tried to take advantage of stuff like spatialization. The piece is written in stereo, so you have two speakers. But with two speakers and enough math and some coding, you can actually make sound appear anywhere in the room, even behind speakers, above speakers, below speakers, in front of speakers, using what's known as a phantom image. And so this piece kind of explores that really to an extreme way.
That's an interesting way to do composition too, because I think people think of maybe a singer-songwriter type situation where you're sitting down and you're just coming up with a tune and lyrics, and you're talking about much more extensive, like almost like an art installation.
Yeah, for sure. And it's not, installation is probably not the right word, but it is a work about that's probably more focused on personal expression, which is, and trying to express in some ways the human experience, as opposed to, say, a pop tune who, let's face it, it can be artistic and expressive and all that, but the bottom line is the pop tune has to sell.
Right, yeah.
I mean, there's a business side to that. There's not a business side, although I am maybe the only composer of experimental electroacoustic music that got into this business for the fame and the money. So
how's that going?
It hasn't worked out as well as I had hoped.
But I couldn't just like play your piece on my computer, right? Because I wouldn't get the same effect because the speaker location matters mathematically.
Well, actually, this piece is built so you could play this piece as long as you had two speakers that were separated.
Oh, okay.
You could totally play it, and if you're sitting in equidistant triangle, where you're one point of that triangle, you would get the full effect.
Oh,
but
awesome.
the piece has been played, I don't know, thousands of times in public, on everything from two speakers up to, a Dolby Atmos system.
Wow.
So, and diffused that way.
Well, from the physicist's perspective, music is a physical phenomenon. That's what you've been describing. It's actually experienced in the physical world by humans. It is a vibration of matter which is sensed by the human body. So in that sense, it is actually, a very physical activity. Without that engagement, for example, there's no sound in space because there's no matter in space. And then the other thing I was listening to is relationships, harmony, ratios, mathematical ways of putting things together. And I didn't fully understand all of this until I actually started teaching the physics of sound. And then I extended to teaching the physics of music, where you're showing, like, what's a chord? What's an octave? And an octave, for those of you, is just simply a multiplication of the frequency by a factor of 2, or a division of the frequency by a factor of 2. So if you have a wave which is 440 beats per second, one octave would then be 880 beats per second. And then another octave would be 1,760 beats per second. It's just multiplying by 2.
Why do I feel like I understand music more now than I ever have before from that?
Yes, and then so harmonies, like thirds and things, are ratios of whole numbers. Well, you take the frequency of one wave and divide it by the frequency of the other wave, and instead of getting an irrational number, you get two whole numbers. Like you could have...
Well, this is pre-1650.
Yes.
Right, because then you get equal temperament that happens.
So this whole notion of dissonance, and so it's interesting because physicists have this natural inclination for harmony, and when we look at the mathematical equations, we want the mathematical equations that describe the physical universe to be in harmony with each other. And so then when you translate that into the musical world, We want the sound waves in the musical piece to be in harmony with each other, and then dissonance creates tension, so that when there's dissonance in the mathematical formulas that describe the physical world, there's tension within the physics community as to whether, what is this? What is it telling us? There's something unusual happening here. And I just think that's an interesting analogy.
Yeah, that's really interesting to me. I hadn't really thought about it, the concept of dissonance and its resolution from a scientific perspective.
Yep. From the mathematics that is used to describe what's happening in the world.
Yeah, I'm thinking about that right now in a piece. I'm working with a colleague who teaches linguistics here, and I'm thinking about it from the idea of dissonance and consonance in relationship to other fields like linguistics. Right? There's a finite number of phonemes that we can find in human speech, and there are some of those phonemes are more used more often than others. And so you can set up a map of consonance and dissonance. I mean, all dissonance is tension, and consonance is, the resolution of that dissonance.
And this notion of resolution in music, and I was just thinking about it right now in physics, I can remember lots of times in the classroom, both as a student and as an instructor, and you're going through a complicated derivation or calculation, and there's just an enormous amount of dissonance on the board in the mathematics, and students aren't exactly sure where this is heading. And then finally, there are some simplifications and substitutions, and then you get the final solution, which feels so much like a resolution. And it's satisfying. And you have this tension of where is this mathematics going, with then all of a sudden, and aha, you do this, and bingo, the problem is resolved. And then in some sense, the feeling that I have as a physicist going through this process, and the feeling I have as somebody who's appreciating music, when you have near the end of a piece and you're not exactly sure what's going to happen, and then all of a sudden the piece resolves, and you're just kind of like, wow, okay, that's neat.
It kind of blows my mind that harmony and what we like to hear together can be broken down so scientifically, and it isn't just like what sounds good to the ears. There's that scientific reason as to why it sounds good to the ears.
Yeah, and this really goes back. There's a lot of theory on this back in the Baroque era, so 1600s, 1750. Rameau, I believe, was the guy who wrote a theory treatise on the harmonic series. So all of our, intervals in the Western world, there's when you have sort of a regular rarefaction and compressions of audio, a tone begins to emerge. So 440 hertz or 440 cycles per second, 880. Those were our orchestra's tuned to 440, which is the A above middle C. And but if you look at the harmonic series, what the harmonic series is when you play one note, what you're really hearing is a whole series of notes above it, right? And it's a natural occurring phenomenon. And as you look at those notes up to so the first harmonic is above the fundamental note that you're playing is an octave, and above that's another perfect fifth, and then a fourth above that, and then the third. And by the time you get up to that, at that point, what you've outlined is a major triad. So like if your fundamental is C, and if we had a piano here, we could totally demonstrate this by holding down a key and pressing another, and you can hear that major chord begin to emerge just from one note. And so your observation is absolutely correct that this is kind of baked into the physics of music, is the sort of major minor modality that we mostly know. The difference is it is changed from what it was, because what happened in the Baroque era was composers wanted to modulate from different keys. So they wanted to play something in C, and then they maybe wanted to play something in G and something in D and something in A through the circle of fifths. The problem is when you do whole divisions, where you have the octave is a 2-to-1 ratio and the fifth is a 3-to-2 ratio. If you go to tune a keyboard instrument in that way, by the time you you go through the whole cycle and you get back to where you started, you're off. And so you have what's known as a wolf note that's out of tune. And so what they do in equal temperament is they make all of the intervals equal. The math behind it is if you know that 440 is an A, 440 hertz, the next note up on the keyboard would be a B flat or an A sharp. To get that frequency, you would multiply 440 times the 12th root of 2, which is anybody?
I used to know that.
Yeah, it's like 1.0549 or something, right? But yeah, so and then to get from B flat to B, you would multiply it also by the 12th root of 2. So I've done a little bit of stuff on this myself, because what we do is we divide our octave into 12 equal steps, and that's where the term equal temperament comes from. What the sort of the ancient Greek stuff like Ptolemy, and I prefer to call him Ptolemy, but would come up with were these whole number ratios like 1 to 2, 3 to 2, 4 to 5, those types of things. But what this does is this, again, that leads to notes being out of tune after you go up a few octaves.
So are pianos like physically constructed differently now?
That's a great question. I mean, the piano didn't actually emerge until after equal temperament. So the piano is actually a relatively new instrument in the world of instruments, because it doesn't really come onto the scene until the end of the 18th century. So you have the pianoforte, I think, is probably around 1760s or so. I'm not a historian, but
you could ask about harps. Are harps made differently today?
Or harps or violins or cellos.
Yeah, but the other part about it is the frequency at which the string vibrates is not just the length of the string, but it's the tension of the string.
Right.
So you can change the tuning of the stringed instrument simply by adjusting the tension to make it be almost anything that you want.
So do they tune differently?
Well, the harp is not a chromatic instrument.
Mm.
So you can't play all 12 notes on a harp.
Mm.
So I don't know the history of construction of the harp, but my guess is that no, the construction hasn't changed, but the tuning has.
One of the quick comments I wanted to make before we end is going back to the whole notion you were talking about the harmonics. And it was always fascinating to me that, for example, a clarinet and a trumpet and an oboe and a piano can all play the exact same quote-unquote note. They can all play the A above middle C, yet all of those instruments sound different from each other. And it's because the harmonics that they create are different.
That's right. So the harmonics, actually, the pitches that they create are the same. The difference is the amount of power or the amplitude of each of those harmonics is different. And it's fluctuating. And those harmonics are going in and out of phase. So you have harmonics that are starting at different points in the cycle. And so you have, that's why we call it timbre, right? Or if you're from Oklahoma, timbre. And what it does is that's what we call our sound color. So this is why an oboe sounds like an oboe and a violin sounds like a violin.
Or a Stradivarius sounds like a Stradivarius.
Yes, absolutely. Or a Guinness tastes like a Guinness.
Because it's like, why is this instrument better than that instrument? And it's because the timbre of that instrument is more beautiful to human ears in whatever way. And scientists have been struggling to try to figure out why that particular instrument produces the harmonics that it does. It just does.
And we don't have more Stradivariuses now, so guess we haven't figured it out.
Hey, before you end, I'll just give you a plug. If you are interested in hearing the Heisenberg piece I mentioned, you can do it on my website at bigcomposer.com.
All right, I'm going to do that. The views, thoughts, and opinions expressed are the speaker's own and do not represent the views, thoughts, and opinions of Lewis University. The material and information presented here is for general information purposes only. The Lewis University name and all forms and abbreviations are the property of its owner, and its use does not imply endorsement of or opposition to any specific organization, product, or service. This podcast was produced in the WLRA podcast studios at Lewis University. Visit lewisu.edu for more information about Lewis University. This has been Science Coast with Mallory Havens and
Chris White.
And our guest,
Mike McFerron.
Thanks for listening.